Okay, this is Math 1151. It's, wait, quiet. Sorry, I know you're having good conversations and all, but now it's time to do calculus. Yep, exciting. Okay, so, good water. It's kind of strange when it has a flavor. Somebody asked me a question from your homework. The problem said something like this: y equals 5x sine x squared, and the question said compute d squared y over dx squared. Now this might be pretty scary notation here, but all this means is take the derivative twice. That's really all it means. Okay, so let's do it. So this is equal to, well, let's, this is equal to d over dx, d over dx, 5x sine x squared. I'm using different chalk today. Maybe it'll erase better. I don't know. We'll see. If you have strong opinions on this at the end of the class, you can tell me or send it in an anonymous email. Okay, so now let's do this. This shouldn't be so hard. So this is the derivative with respect to x of, well, whatever this is. So what rule do we have to use first here? The product rule. So we take the derivative of 5x. That's going to be 5 times this thing times sine x squared plus, and now what we're going to do is take the derivative of this thing. The derivative of sine is cosine. Cosine of x squared. And now I'm using the chain rule. I have to multiply by the thing on the inside, so that's going to be 2x. Outstanding. That looks great. What'd I do? I forgot the 5x. Oh, plus 5x times this. Thank you. Whew. But now we have to do the whole thing again. We have to do it all again. And so this is going to be equal to, so now we take the derivative again. It was so much fun the first time. Again, and that's what this means. It means just take the derivative twice. So first, we have 5 times sine x squared. Well, that's not so bad, right? So that's going to be 5 times the derivative of sine is cosine x squared. Now I take the derivative of the inside. I'm applying the chain rule times 2x. That's the derivative of this term. And now I take the derivative of this term. Now it's going to help if I simplify this a little bit, probably. So let's go ahead and do that. This is equal to 10x squared cosine of x squared. So now I'm going to take the derivative of 10x squared cosine x squared. I have to use the product rule again. And so the derivative of the first part is 20x. The derivative of 10x squared is 20x. So it's going to be 20x. And now this piece stays the same, cosine x squared times cosine x squared, plus, now this piece, the 10x squared, nothing happens to it. 10x squared times the derivative of cosine x squared. The derivative of cosine is negative sine, right? So that's going to be minus sine x squared. And now, what rule must I remember to apply? The chain rule times 2x. Oh, goodness. That is the second derivative. Yes. You have another question about the homework. What is it? Wait. Before, I won't forget your question. Can I just make sure everybody understands this first? Any questions about, yes? He says right here, this 5 right here, why does it happen right here? Well, the short answer is that's the constant multiple rule, right? When I want to take the derivative of 5 times f of x, it's equal to 5 times f prime of x. That's the short answer. The longer answer is, well, you could do the product rule, but you're going to get 0 times f of x plus 5 times f prime of x, right? Any other questions about this before I entertain another question? Do you need to simplify this answer? No. No. Good question. What's your question? Determine the slope of the following curve at the given point. Okay, let's see if we can muddle through this one. What is the curve? Let's see if we can figure out what's the curve. Can you tell me that? 3xy to the 1/3 like that? Yeah. Good. Plus 4y equals 15. And what's the point? That 16? That too. Okay, 16. The coordinate is 4, 1. So we want the slope of the tangent line to this at this place right here. What type of differentiation are we going to use? Implicit. We're going to use implicit differentiation. Implicit differentiation. And while that might seem scary at first, it's really not so bad. Let's allow me to erase. Well, I'll just start working right here. Okay, so with implicit differentiation, you pretend that y is a function of x, and you use the chain rule. So, and the product rule if you must. So for this first one, let's do it. I want to take the derivative of everything. So I take the derivative of both sides. So I'm going to write d over dx of 3x y to the 1/3 plus 4y equals, what's the derivative of 16 with respect to x? 0. 16 doesn't change at all. 0. And so now I have to take this derivative here. Uh-oh. Okay, stay calm. Let's see, product rule. The derivative of 3x is 3. So it's going to be 3 times y to the 1/3 product rule, right? Plus 3x. And now I take the derivative of y to the 1/3. And let's see, the 1/3 is going to come down like so. And y, what's 1/3? What's 1/3 minus 1? Oh, negative 2/3. That's right, negative 2/3. That's good. Yeah. I don't know what the question is. She says, she's telling me that she thinks it's this. Okay?
I thought it was on homework, and that's probably why I got it wrong. So how did you know to only take y to the 1/3?
How do you know to only take y to the 1/3? Like I said, I had no idea what the question was. It was a lucky chance. If it's x, was it written like so? If it doesn't have parentheses, the exponent only affects the thing that's closest to it. Does that make sense? Exponentiation is stronger than multiplication. It's more glued tightly together. You do it first. Do you think this is right? Are we doing the right question? She says yes, I believe her. You know, one way you could check is you could plug in 1, 4 here, 4, 1 here. And if you get 16, then you're probably doing it right. Let's double check that, because this will be a disaster if at the end of the day, this point isn't on this curve. Let's just check it real quick. What's 1 to the 1/3? Usually it's 1. And then what's 3 times 4? 12. 12 plus 1 is 12. 12 times 1 is 12. Plus 4 times 1 is 16. Oh, okay, so this looks good. This looks good. I'm going to go ahead and finish this problem. By the way, what do I have to do right here? I have to do something. I have to multiply by y prime or some such. So I'll put y prime there. Times y prime. Oh yeah, I have another term here. Plus 4y prime equals 0. So there, I think I just used implicit differentiation to take the derivative here, I think. All right, so I guess we could simplify a little bit. Let's do that. So 3 times y to the 1/3 plus these cancel, xy to the minus 2/3 times y prime plus 4 y prime equals 0. And now what do? We get our y primes alone. We solve for y prime. Solve for y prime. Solve for y prime. In the back, what do you think? Is the chalk as readable as it usually is? Yes? No? It's better? Worse? Same? Stop talking, Bart, and keep on solving that problem. Okay. We put these on the other side so we get, oh, not this one. This one stays right here. Xy to the minus 2/3 times y prime plus 4y prime is equal to minus 3y to the 1/3. Is that correct? Is it okay? Is that? All right, so now I can factor out a y prime times xy to the minus 2/3 plus 4 is equal to minus 3 y to the 1/3. And now I divide both sides by xy to the negative 2/3 plus 4. Y prime is equal to minus 3 y to the 1/3 all over xy to the minus 2/3 plus 4. There's my derivative. How do I find the slope of the tangent line? I take those numbers there and I just plug them in. Right? The slope of the tangent line, the slope is equal to nice big, y to the minus, the numerator is minus 3. And the denominator is, the denominator is 8. Is that right? Minus 3/8. Look good? Yeah. This 3 and this 1/3? No, because this is in the exponent. This is outside. No canceling goes on there. Yeah. It'd be nice if we could. Math would probably be a little bit more simple. Yeah, I'm sorry. How did I get the 4y prime in the second line? Let's see. So I got this one right here, but I got it from here. But where did it come from? It came from here. So this is 4y. And so when I take the derivative of 4y, it's the constant multiple rule. It's just 4 times y prime. You were probably looking for it to come out of some of the other things. It's all right.
Could you also take xy to -2/3 over to the other side as well?
Could I have taken xy to negative 2/3? Well, it's multiplied by y prime here. So, no. Is it good? Is it okay? The person who asked the question looks so sad right now. You okay? Is all right? Okay, good. All right, so let's see. This is good stuff. This is good stuff to go over. But today, I'm supposed to talk about something else. Now, I want to tell you, I do not see it as my purpose to take everything in the textbook and put it on the board. So there's going to be some stuff I'm going to say, hey, look that up. All right? It's just not very efficient to do it that way. I'm just going to try to, my idea is, I'm more like a guidebook. You should go look this up. Like when you go to New York, you should go here. When you're studying calculus, you should make sure you know this. Make sense? You should make sure you know everything. Done. No, that's not helpful. All right, so let's start with. There's a couple functions we don't know how to take the derivative of. One of them is arctan. Now, arctan. I'm going to do something a little bit strange, I guess. Oh yeah, Bart, think, Bart. Oh geez. I'm going to do something a little bit strange. When you take tangent of a function, right? When you take tangent of a function, what sorts of things do you plug in to tangent? Angles. You plug angles into tangent, right? Tangent accepts angles. And the letter that we use for angles a lot of time is theta. You make theta by making a little egg shape, and then you make a little line. That's how you do it. That's how you make a theta. So tangent of theta, right? Great. Let's see. I want to make sure I don't want to screw this up. I probably, whatever. Okay, so what does tangent of theta look like? Well, tangent is sine over cosine, right? I think it looks like this, right? Looks like this, and tangent of theta, and I hope I'm scared right now. Well, I'm just going to put it down. If I screw it up, we'll figure it out. There, I think tangent looks like this, doesn't it? And what tangent is sine over cosine, right? Tangent of theta is equal to sine theta over cosine theta. And cosine theta is 1, and it's 0 at pi over 2. Isn't that right? That cosine of theta is 0 at pi over 2 and negative pi over 2. All right, so great. So this is going to be minus pi over 2. It's an asymptote. And here is pi over 2. That's another asymptote. This should be going more straight up and down, but that's fine. So what do we want to call this axis? I'll call that axis y. So we have the theta axis and we have the y axis. Excellent. So now, if I'm talking about arctan, and this is, I'll label my stuff real quick. This is tangent, tan of theta. Arctan of theta. Arctan of theta, what's arctan of theta look like? It looks like, you take this thing, it looks kind of like this, doesn't it? That's arctan. Arctan. What's another notation people use for arctan of theta? Tan inverse. And why is that no good maybe? It looks like you're saying 1 over theta, right? If you ever see that tan inverse, it does not mean 1 over theta. It means arctan. And the really good question would be, how do you know, right? Well, if it's closest to tangent, it means arctan. If it's outside and in parentheses, then it means 1 over. Hopefully nobody ever uses it. I have a theory about why people started using tan inverse, and I'll share it with all of you. You're like, I don't care, Bart. Okay, you know, like the TI-82, I think calculator companies started using tan inverse because the words arctan wouldn't fit on the button, actually, and tan inverse was smaller. But it makes things more confusing. So here we go. We got our functions. We got our inverse functions. Tan inverse, arctan. What the heck is the derivative of arctan? You gotta be a little bit careful here. So arctan of theta. No, sorry. Arctan. What does arctan accept? Arctan should take in. Oh my God. Arctan should take y's. It's weird to put these all in the same plot. I'm sorry, guys. Here, erase this. If you wrote this down, it's not wrong. It's just confusing. What does arctan look like? Arctan looks like if you take this thing and you do this to it. You reflect it across, right? That's what arctan looks like. And your axes should change. This is the point I was trying to make. What we should do then is arctan undoes tan. So you should have y here. Arctan outputs thetas. Tan takes angles and outputs numbers. Arctan takes numbers and outputs angles. That's what I was attempting to get at. I'm sorry, I didn't do a very good job at it. Okay, and then here, so there's arctan, and these are angles, and that's better, I think. It makes more sense, right? Yeah, you shouldn't put them on it's bad to put them on the same axis because they do different things, right? They conceptually. There's nothing mathematically wrong with them on the same axis. This is conceptually, it's kind of strange. So look, if arctan of y equals theta, that means that tangent of theta equals y. Yeah, I'm sorry, what's up?
Your graph of tangent theta, it has going towards going up the y-axis, and then the graph of our tangent theta is also going up the y-axis. Did you just redraw tan theta on the side?
I did.
But when you drew it on the same tangent theta.
It's true. It's true. He says he's the same thing, right? He says he's the same picture. What? Okay. You're right. What? I'm going to try to reconcile this in everybody's head, okay? Does anybody remember the definition of inverse function where you just reflect over the line y equals x? Do you remember this? Oh, you just take the function and you reflect it across the line, y equals x. What happens when I reflect this, including the axes? And all I'm trying to say is you plug in thetas here and you get out y values for tangent. And for arctan, you plug in y values and you get out thetas. Yeah, so he says, Bart, it looks like you just took your picture and then did this to it. And my answer is yes, that's exactly what I did. That's a good point. No, it's not so mysterious maybe. I just turned my head. Well, I didn't turn my head, I reflected. It's different. Okay, so arctan of y equals theta means tan of theta equals y. And yeah, of course, because look at the picture. Okay. So now, what we're going to do is we're going to start here, and we're going to use implicit differentiation. And I'm going to throw some notation at you that maybe you haven't seen. Okay, so I'm going to say, take the derivative with respect to y of tan theta on both sides. So d dy of y. So we're using implicit differentiation. We're pretending that our theta value is a function of y. Well, what's the derivative of y with respect to y? The derivative of any variable with respect to itself is 1. That's equal to 1. What's the derivative of tan theta? Secant squared. Secant squared, oops, got to put a c in secant. Secant squared theta, chain rule, times theta prime. Now we solve for theta prime. Theta prime is equal to 1 over secant squared theta. Yes?
Why isn't it the derivative of theta with respect to y?
Why isn't it the derivative of theta with respect to y? It is the, okay, that's a good, d over dy of theta. That wasn't your question.
In the actual problem, why didn't you write? Because whenever you do like the y prime, like the right y prime, you write the derivative of y with respect to x.
Aha!
So I'm wondering why.
Can I repeat your question? So she says, usually when you do this part, you have x's and y's around. You take the derivative with respect to x, and you write dy over dx. But now what you're doing is your y is in the bottom, right?
That makes sense.
We're pretending, usually, when we do implicit differentiation, we pretend that y is a function of x. And so we take the derivative with respect to x, and every time we see x, the derivative with respect to x is 1. But now, theta is a function of y. Theta, this is theta right here, and it is a function of y. It's arctan of y. So we're going to take the derivative with respect to y. And so we'll write d theta dy.
I was just wondering why. Well, I was wondering usually when you.
Did I answer your question?
I'm just wondering about the notation. Why you don't write it as d theta.
Oh, she's asking this. She says, you wrote this, Bart. You wrote d over dy theta, right? As opposed to d theta over dy.
Yeah,
Yeah, they're equal. They mean the same thing. They mean exactly the same thing. Okay, so 1 over secant squared of theta. I want my answer to be in terms of y, not thetas. So look, last time we went back to the first day of class with logarithms a little bit. Today we're going to go back to the first day of class with triangles a little bit. So look, I know that tangent of theta equals y. Can we draw a triangle with theta here and tangent of theta equaling y? Yeah, tangent is what? Opposite over adjacent, is that right? Opposite over adjacent, so y over 1, right? And what's the, secant. Secant is 1 over cosine, right? And cosine is adjacent over hypotenuse, isn't that right? So I need to know the length of the hypotenuse. So this is going to be the square root of 1 squared equaling 1 plus y squared, right? So what's secant squared equal to? Or what is this? So this is equal to, secant's equal to this over this. So secant squared is just equal to the thing on the inside. So this is equal to, so d theta dy is equal to 1 over 1 plus y squared. D theta dy is equal to derivative with respect to y of arctan of y. So what's the derivative of arctan of y? It's 1 over 1 plus y squared. What's the derivative of arctan of x? 1 over 1 plus x squared. This is weird, right? It seems like arctan, yeah, go ahead. Yeah, so this is equal to 1 over the square root of 1 plus y squared squared. So let's write this down over here. I think I can still see this in my camera. We'll find out. D over dx arc tan of x equals 1 over 1 plus x squared. All right, let's do arc sine. See if we can get the hang of this, right? And then we'll do arc secant, and then those are all nasty. All right, so here we go. Let's see. Are we ready to do the next one? Okay, so arc sine. Well, what does sine do? Sine takes what type of numbers does sine take? It takes angles. Sine takes angles. So sine of theta is equal to y. Well, that happens when arc sine of y is equal to theta. If arc sine of y equals theta, then sine of theta equals y. They undo each other. And so now we're going to pretend, we don't need to pretend very much. We know that theta equals arc sine of y. So theta is a function of y. And I know that sine of theta is equal to y. Let's take the derivative on both sides with respect to y. So we have d dy of sine theta is equal to d over dy of y. Remember, the derivative is asking how much does this function change with respect to another function. How much does this variable change with respect to another variable? So y is changing with, as y changes the same amount, right? So this is going to equal 1. And sine theta, well, that's going to be derivative of sine is cosine. Cosine theta times d theta dy times the amount that theta changes with y. Okay, so fine. D theta dy is equal to, d theta dy is equal to, 1 over cosine theta. I didn't put any parentheses here. I don't know. And d theta dy is, well, whatever. It's good. But now we have to write that cosine in terms of y. What do I know? I know sine theta equals y. So I'm going to draw another triangle. I'm going to draw another triangle. I want a triangle. And I want sine theta to be y. Sine is opposite over hypotenuse, right? So I put the y here, the one here. What goes here? Square root of 1 minus y squared. Outstanding. There we go. Oh, let's put one more piece of labeling on this. Put theta there. Aha! So cosine is adjacent over hypotenuse. So d theta dy is equal to 1 over square root of 1 minus y squared. This is equal to the derivative of arcsine. Arcsine of y. So now I'm going to write it over here. D over dx of arc sine of x is equal to 1 over square root of 1 minus x squared. So as far as basic functions to differentiate, what are the hardest to do? These inverse trig functions, right? They all look kind of like this. You're going to have to memorize them. Let's do one more. I'm going to post some practice exams from other universities. I hope that helps, okay? I'll post that. And maybe I'll even post some derivative tests. Of course, the exam's going to be much harder than just a basic test on derivatives, but you could at least practice a bunch of derivatives and make sure that you know everything then. Yeah, what's up? Why is this equal to this? Right? She says, why is this equal to this? It doesn't look the same. Well, theta is equal to arcsine of y. And so all I'm doing is taking the theta here that I see and replacing it with arcsine of y. This is really kind of subtle. This is kind of... Does anybody... Let me ask you this. Does anybody want to see me do this thing with secant, or do you just want to see some derivatives practiced? How many people want to see the secant thing? Raise your hand. 3 or 4. How many want to see some derivative practice? Yeah, we have it. Thank goodness. Okay. Okay. Look on page 2. So to look at... We've done 2. That's the basic idea. They all follow this way. Sometimes instead of drawing a triangle, what you do is you use like a Pythagorean identity. But seriously, I don't think we're going to ask you on the test how to derive these things. We're just going to expect you to know it. And if you're ever in the situation on the test where you have to derive it, you're in trouble. Okay? So you should really know these inverse trig functions. Or you should just chalk it up to acceptable loss. You know? Well, I'm just going to miss that problem. I shouldn't say that as a teacher. You know? But let's be realistic. You know, you're studying, you got to decide what's most important, right? No arctan. That's everybody's favorite to ask. No arcsine, no arc cosine. Then no arc secant. Then no arc cosecant. And then no arc cotangent last. All right. So here we go. Here's the derivative. Are you guys ready? Here's a hard derivative. Take the derivative with respect to x. Because this, by the way, we're at the end of our derivative rules at this point. So I'm just going to start combining a bunch of them and see if we can do them. That's the idea. How about this? Log base 5 of x plus 1 over the the cube root of x. How do we take the derivative of this with respect to x? What do we do here? Does anybody know what to do with that log base 5? Well, natural log of x over natural log of 5. So you rewrite this. This has a trick to it. You rewrite all these things. So this, whenever you see log with another base, right, you write it as natural log of x over natural log of 5 plus, and what do you do with this? You rewrite this too. This becomes x to the minus 1/3. Is this derivative looking a lot easier now? I hope so. I really hope so. Because this is just a constant right here. What's the derivative of natural log of x? 1 over x. So this equals natural log of 5 over x minus 1/3 x to the geez, minus 4/3. Did I do that correctly? Whew. All right, let's do another one. We are literally just going to try to see if I can throw some derivatives at you that are a little bit harder at this point. All right, let's do this one. 2x cubed minus x squared secant of x. 2x cubed minus x squared secant of x. Is this one, what do we have to use here? The product rule has to happen first. This question is basically testing to know, do you know the product rule? Let's do it. So we take the derivative of the first thing here, and we get 6x squared minus 2x. All times, what's the derivative of secant of x? Don't do that yet, Bart. That's right. Trick question. I have no idea what's going on. Okay, so now 2x cubed minus x squared. Aha! What's the derivative of secant of x? Yeah. Secant x tangent x. Secant of x tangent of x. Expect the exam. On the exam, you should expect them to throw as many of these trig things at you. You know, like, they're not going to ask you something easy. They're going to ask you something like, oh, you think you're pretty smart? Okay, take the derivative. Let's do one. Huh? Yeah, I'm ready. Okay, here we go. If I was writing the exam and I wanted to put a devilish question, I don't know. I'm not somehow evil enough to come up with some of these questions. Oh yeah. Okay. Arctan of natural log of x squared. Boom. Right? Does that look pretty bad? 3 to the x arctan natural log of x squared. Take the derivative of this. Let's do this one. All right. Are you guys ready? What rule do we use first? Product rule. What's the derivative of 3 to the x? Three to the x natural log of 3. 3 to the x natural log of 3. So it's going to be 3 to the x times natural log of 3 times arctan of natural log of x squared. 1, 2, that's good enough. Okay, oh, but I'm not done yet, shoot. Okay, plus, because I'm doing the product rule, plus, what's this one going to be? Oh, now I have to take the derivative of this stuff. Oh my God. So now, the derivative of arctan is going to be 1 over 1 plus this stuff squared, natural log of x squared, times the derivative of natural log of x squared. What's the derivative of natural log of x squared? 2x. This wasn't so hard. 2x over x squared. Done. What do you guys think? No! Okay, so here we go. 3 to the x. Good. What do you guys think? Is that a tough problem? Are we ready to do another one? Any questions about this one? Can I go over where I got 2 to the x over x squared? Yes. This is the derivative. This is equal to the derivative of natural log of x squared. Because remember, you got it now? The derivative of natural log of f of x is equal to f prime of x over f of x. All right, let's do another one. Let's do okay, here we go. I got this one. Two to the x plus 3x all over natural log of 2x minus x cubed. How do we do this one? It's the quotient rule. The quotient rule. We could use logarithmic differentiation, but we're just going to plow through it with the quotient rule. All right, let's do it. The quotient rule. The quotient rule. Quotient rule. Take the derivative of this using the quotient rule. Okay, quotient rule. You know, you take low d high, right? Low d high. So this is equal to, well, the first things first, I guess in the denominator, I can just square the stuff, right? Write that down. Okay, I'll do that first. Natural log of 2x minus x cubed all squared. Okay, that's fantastic. I'm like halfway done because I got the denominator. Low d high. Okay, so now I write this down. ln of 2x minus x cubed. Okay, d high. Okay, so now, what's the derivative of 2 to the x? 2 to the x natural log of 2. 2 to the x times natural log of 2 plus what's the derivative of oh yeah, 3x plus 3. That's easy, Bart. Why are you freaking out about that? Okay, so now plus, and that was low d high, now I do high, 2 to the x plus 3x, but minus, that's right, minus, we're doing the quotient rule, minus, wow, minus d low. Okay, so now I take the derivative of the thing in the denominator, and so now this is not so bad. This is 2 over 2x, isn't it? You could just write 1 over x if you wanted to. 2 over this minus 3x squared. It just occurred to me that I have a word problem I want to do as well. So let's do this word problem. How much time do I have left? Timer, alarm. I have 2 minutes. I have at least 2 minutes left. So let's do this word problem real quick. Oh, we're done with this. This problem is done, by the way. Right? Does everybody agree? Does anybody agree? Let's do this word problem. It's number 35 on page 217. It's not a very hard word problem, but it's kind of it's a little different than what you might be used to. So let's do it real quick. You're on a boat. Maybe you're in what's the lake? Maybe you're in that Great Lake by Chicago, and is that Lake Superior? Michigan? Okay, Lake Michigan. And here you are, and there's some building, and here you are. This is a boat. Here's a boat. There you are, and there's an angle theta, and your number 35, page 217. Your boat's 500 meters from the building. The building's 150 meters tall. 150 meters tall, and you're 500 meters out, and we want to know. Oh no. We want to know how theta is changing with respect to x. As you move your boat in and out, the angle that you see with this building, right? Does that make sense? It's changing, right? So how do you do this? It's not too hard. What is theta in terms of x? How do you find theta in terms of x? Sine, tangent. Shouldn't we use cosine of? Isn't cosine of theta equal to? Jason over hypotenuse. Tangent. You're right. Tangent of theta is equal to opposite over adjacent, 150 over x. Right. And so what we want to do is we're going to take arctan of this. Arctan of 150 over x is equal to theta. So if they're asking you how fast theta is changing with respect to x, you take the derivative of this. And what's the derivative of this? What's theta prime then? Or d theta dx? D theta dx is equal to 1 over 1 plus 150 over x squared times the derivative of what's the derivative of 150 over x? (150 minus 150 over x squared). This is number 35 on page 217. All right, we're done. Have a nice day.